Okay, good morning, everybody. I'm Martin Ralph, Chair of the IMechE Food and Drink Engineering Committee, and we're here for the presentation on optimizing pump systems. You should be able to see the first slide in front of you. I was a bit surprised when I saw the picture. I thought, what a big picture for a little tiny pump in the middle. But then I noticed the big pump on the right-hand side, which is a little bit special. Anyway, Grundfos pumps are the biggest pump manufacturer in the world. There's something like 19,000 employees worldwide. And we've got two speakers, Charlie St. Lawrence and Rhett Johns, who are going to give us a talk today on achieving your sustainability and net zero targets through optimized pump systems. Okay, so we'll just give people a few more minutes before we start up. Another couple of minutes maybe. We're already quite a few people here. Okay. So this is part of our the IMechE plan to educate. Maybe that's not the right word, but educate newcomers to the industry and older people who want to know a bit more about pumping systems, and it's more to do with the control of pumping systems than the actual pumps themselves. So I'm looking forward to this myself. Could you go on to the next slide, please? Okay, this is just a little bit of housekeeping. The event will be recorded. In fact, is already being recorded. So if you're not happy with that, I suggest you sign off now, but hopefully it's okay. And we have disabled all the media for attendees to make it a smoother operation. If you want to ask a question, and we'll look forward to receiving your questions, please go on to Q&A. Okay, we will keep an eye on chat, but Q&A is the main area for questions. Okay. What we will, there is a disclaimer on there that the content of the event and the presentation slides are solely for the use of delegates, both for business and for your own personal use, but please do not share them with other people without express permission of the IMechE and the speaker or the speaker. Okay, so we will put up the presentation onto our YouTube channel, and that will be described how you can get onto that later on in the presentation. Okay, so I'm going to hand over now to Charlie St. Lawrence and Rhett Johns of Grundfos. Thank you.
Thank you very much, Martin. Good afternoon, everyone, and welcome to our presentation on achieving sustainability and net zero targets through optimized pump systems. And I would like to say thank you very much to the team at IMechE for inviting us to present on their platform and for taking this very interesting and important topic to you all. My name is Rhett Johns, and I'm the sales manager for UK, Ireland, Belgium, and Netherlands for our projects and energy optimization team. I manage a team of engineers working with the consultants and EPCs on new build for factories and large expansions, as well as in our energy optimization and audit team that audit existing factories and facilities for finding energy optimization within pump systems. Joining me here today is Charlie St. Lawrence, our business development manager for consultants and EPCs in the UK.
Yeah, hi everybody. Again, just to echo what Rhett said, thanks very much to IMechE for letting us present on their platform. And yeah, I'm really looking forward to presenting this with Rhett. Pumps and pump systems are working away behind the scenes, in many cases 24 hours a day. Many of us don't see them, but they are the lifeblood holding up our industries, our commercial and our domestic buildings. at Grundfos, this is something that we see every day. So we have a really good understanding of the importance that our pump systems are optimised and not wasting unnecessary energy or water, and that's what we're going to look at today. And as mentioned earlier by Martin, please put any questions you might have in the text box, and we can go through these at the end. So we'll start with an introduction and just give you a quick general overview of Grundfos. Then we'll look at our sustainability ethos as a business and how we're reducing carbon emissions across our value chain, and explain our sustainability accreditation with science-based targets, who they are and how they influence the industry. Then we'll dive into how to build a sustainable pump system, understanding the main factors and the influences to efficiency. Then we'll look at intelligent design and system control, explaining what is meant by pump intelligence and again how this is the key to an optimised, efficient system. We will also be touching on the importance of water reuse, as this is another key aspect of sustainable operation and the regulation around that. We'll show you how we measure and analyse energy use for existing installations with our energy optimisation analysis, and then finally we can look at some excellent examples with customer cases. So a very quick overview of Grundfos. As you can see, we are the #1 pump manufacturer in the world, and that is based on units sold every year worldwide. We have a global presence operating in numerous territories, as you can see on the screen on the right-hand side there, and we're active across all areas of industry. So food and beverage, energy, hydrogen, pharmaceuticals, electronics and semiconductors, you can see there. So we really are very present, like I say, across all areas of industry. It's quite common that most people only know Grundfos as a pump manufacturer. But we have come a long way from humble beginnings as a single stage pump manufacturer to where we are today, offering complete pump systems, package solutions and control intelligence. And most of the industrial projects that we're involved with, pumps are only a small part of our scope, where we're usually supplying much more. And then also there, we work with companies Eurowater and IMechE, who are experts in water filtration and purification. And they're a key part of our industrial product portfolio, which we'll touch on a bit later in the presentation.
So sustainability and net zero targets, it's become a very big focus for industry over the last number of years. And the reason behind this is that there's an organization called Science-Based Targets, and they are the new standard for net zero targets in industry. This is a non-profit organization that was formed out of many different independent scientific organizations that joined to form a new standard for net zero targets for corporations about 5 years ago. Science-based targets provide a clearly defined pathway for companies to reduce greenhouse gases, helping prevent the worst impacts of climate change and future-proof business growth. Targets are considered science-based if they are in line with the latest climate science deems necessary to meet the goals of the Paris Agreement, limiting global warming to 1.5 degrees above pre-industrial levels. Many of the largest companies in the world are part of the Science-Based Targets initiative and are aggressively pursuing net zero targets to stay accredited with the body. And that really is the big differentiator. If you are signed on to Science-Based Targets, you can also, there's an accreditation process to sign on. It takes a number of years to get approved by the independent body. And once you're on, you can also get kicked off, which we do see for a lot of large corporations that promise a lot, but they don't deliver at the end of the day. So it's a continuous effort to stay on this ever-evolving necessary targets in order to reduce our emissions gases. So this is the new standard, and many of the largest companies, like I mentioned, like Coca-Cola, Microsoft, Intel, Eli Lilly, are all part of this organization and signed on in order to reduce their energy and their emissions. So something that's very important for us to define is the scope of emissions. So what we call emissions within any value chain for a corporation would be defined as scope 1, 2, or 3 emissions. Essentially, Scope 1 emissions are those direct emissions that are owned or controlled by the company, whereas Scope 2 and 3 are indirect emissions and are a consequence of activities of the company that occur from sources not owned or controlled by it. So Scope 1 emissions are direct emissions that result from activities within the organization at their facilities or maybe with their vehicles. And this can include fuel combustion, manufacturing and process emissions, refrigeration losses, or company vehicles. Scope 2 emissions are those that are caused indirectly and come from where the energy it purchases and uses is produced. So a good example would be a shift from a coal-based energy supply to a photovoltaic or wind farm energy source for your factories. Grundfos has recently achieved, in Europe at least, 100% renewable energy production on our sites, which is a good 5 years ahead of target for ourselves. And then Scope 3 encompasses emissions that are not produced by the company, but are the result of their assets owned or controlled by them, as well as the products that they sell. So for us at Grundfos, a good example would be our actual factories and our company vehicles only present 1% of our emissions, whereas 99% of our emissions come from the energy consumption of the pumps that we sell into the industry and into households, into corporate buildings. So that's kind of how it's defined. And for a lot of companies, that would be how it looks, except for a manufacturing company. For them, Scope 1 would be the primary focus for them to reduce their emissions. Charlie?
Oh, sorry, guys, I put myself on silent. Bringing this back to Grundfos and how Grundfos relates to industry. So, in a nutshell, we're experts in everything water. We don't supply process pumps. We are focused more around the utility side of industrial applications. And as I said, we're involved in across all areas. So, in terms of applications and service, heating and cooling, boiler feed, industrial wastewater treatment and water reuse. And within the utility side of industry, there is a huge amount of water consumed. If we take just the pharmaceutically, for example, there's something in the region of around 50% of the water that's being consumed is actually just going to the utilities. So it gives you an idea of the major role that utilities play and the impact that they have, and the importance that, the focus. I think obviously sometimes we're looking a lot at the process side of it, but actually the role that, as I say, that utilities that the utilities play, and why it's just as important that we have that focus on ensuring that we're running in an efficient way on that side. And again, to try and put some numbers around this, Rich. I'm going to jump to the next slide. So you can see there water consumption in industry. As you can see, in industrialized nations, industries consume more than half the water available for human use. This really underlines the importance of why we're using water in industry in a sustainable and efficient and also a responsible way, and why there is more focus being put on this across the board. And again, this industry uses a lot of energy as well. So these are the two focus points: water and energy. And again, you can see on the screen there. So by 2030, energy consumption in industry is expected to grow by 35%. So these are huge numbers, and 38% of the global total energy use comes from the industrial sector. So, and again, to sort of bring that on further and back into pumps and pump systems. So of that 38%, 10% of the energy is consumed, is related to pumps and pump systems. And where this is really important about this particular topic in optimized pump systems, so worldwide, many systems are not running in an optimized way. And where there is now this key focus on reducing carbon emissions, and the major contribution made by pumps and pump systems. So if we were able to say click our fingers and immediately optimize those systems, all pump systems globally, we would be able to reduce that 10% down by 4%. So this is roughly the equivalent to the energy use of around about 1 billion people. And so this is why what we're going to look at now is how to build an energy efficient system, and the key factors that we need to focus on to make sure that our systems are optimized, and the ways that we can do that.
Yeah, just a small correction there. I think Charlie misspoke. We do processed pumps. We just don't do hygienic pumps within industry. But he's 100% right that processed pumps consume far less than your utilities pumps. So if you're looking at optimizing your factory, that would be the first place that I would suggest anybody to start. Right, so how to design a sustainable pump system. Really, it's covered by 4 steps, and you can think of it starting as start small and work bigger and bigger and bigger. And working outwards from the pump, you can start saving more and more energy in your system. So the first one is selecting and using an IE5 motor, and preferably integrated motors will integrated VSTs on your motor will allow for a 10 to sometimes 20% reduction in energy depending on the size of the motor. Your pump hydraulics, when we talk about efficient pump hydraulics, we're talking about correct sized and running of the correct area of the curve of the pump, and we'll explain that a little bit later. That's going to increase your potential possible savings up to 40% on your system. And then looking at pump systems, when we talk about a pump system, we're looking at multi-pump control, where we've got some sort of a control standard on it, like a pressure control, temperature control value that we're trying to target our pumps running towards. And then we look at complete pump systems. When we talk about complete pump systems, we can go up to a complete system with 90% potential savings. And in these sorts of systems, your pump controller, like you see in the pumps that's at the bottom left, what they're doing is that they're working within the wider net of the system, communicating with the machinery such as the boilers, the chillers, to run and pump only at the required flow of pressure demand that these systems have got. So that's your 90% of your potential savings within the system. That's not necessarily that we can reduce energy consumption by 90%, but if a system has got potential to reduce energy by 60, 70%, you would need to be looking at each of these individual components. So it all starts with the motor. Permanent magnet motors don't require induction to drive the motor and are able to maintain the highest part of the efficiency load in variable pump volume and systems. The industry standard that we see is IE3, and this is something that you are most likely familiar with as a standard. Super efficiency IE4 is also gains efficiency versus the IE3. Through more robust stator windings, more copper used than IE3, and in some cases they use permanent magnet motors as well, though less than your full permanent magnet motors. And then the final top tier that you get is an IE5 motor. So an IE5 motor is the highest standard that you can get currently qualified within industry, and you can get up to 10% additional energy savings just by converting to a permanent magnet motor that has the IE5 efficiency standard. When we look at the yearly energy consumption index of a pump system, if you're running your pumps at 100% load, standard fixed speed motor, you're going to be consuming then 100% of the potential energy consumption on that system. If you then add in your standard induction motor and you have a reduced speed, so you tune the pump speed in order to run it at the required pressure, let's say, of the system, but you don't add any more controls, you've got then a pump that's running at a lower speed, and you can get 32% of your savings that way. The next step for 22% savings, you would need to then go towards that IE5 motor efficiency, but also start looking at adding in sensors and controls in order to efficiently ramp up and ramp down the motor operation in order to run the pump according to the required flow and head that it needs within the controls. So that then really gives you your full scope of savings when we look at optimizing a pump system.
Yep, and the efficient pump hydraulics. So Another crucial aspect of system design is that we ensure that our hydraulic selections reflect the most common operating conditions of our system. So, for example, it's quite common for a pump supplier to select their pump so it's running its most efficient based on the max rated conditions of the system. And my background is actually working for a pump supplier, and I can sort of say from experience that if we are just focusing on the supply of the pumps, that is very commonly the way that that pumps get selected. However, the question we must ask is how long and how regularly will the system run at max conditions? So if that situation will only occur 5% of the time, then we want to make sure that our pump is selected so it's at its most efficient, where we'll operate 90% of the time. And that's what you can see on this system curve on your screen. That's where, again, that's where our pump is going to spend most of its time operating, is at normal conditions. So again, if it's running at its most efficient, it's been designed to run at its most efficient. When it's running at its max conditions, it's not going to be running as efficiently as we want it to. And if you look at our curve, on the right, you can see the relationship between flow and efficiency, and how it's at its most efficient at the duty set point, and efficiency drops off as flow is reduced. So again, we want to make sure that when we're selecting our pumps, that we're selecting them with our most regular conditions in mind, and not the rated conditions, which is a common mistake that we know from pump suppliers when they're selecting pumps.
Yeah. And a common method just to add efficiency to pump hydraulics, it would be to have a look at that best efficiency point of the system, and split the load of your pumps, split the flow of your system over multiple pumps, then switching off the extra pumps as your flow demands reduce, so that it's continuously running at the top end of efficiency per pump. This is an example of a multi-pump system on the left. Sorry, Charlie, back to you.
Yeah, and there are various ways of controlling pumps. So you can see on the right the common methods consisting of throttle control, bypass control, and speed control. The first two are more traditional methods. So throttle control is where we're using a valve to limit the flow. But there are two inherent problems with this, and that is the unnecessary power consumption and excessive pressure in the system. So we know as we start to close that valve, what's going to happen is our duty point is going to sort of move up the curve. But obviously the pump is still running. It's still going to be running and using all of that power that we don't need. We've actually used the valve to change the pump performance there. We haven't changed anything in the pump itself. And then you go down to bypass control. So this is when we recirculate flow when it's not required. Again, two issues we have with this method. The first is the unnecessary consumption of power when it's not required. As I said, the pump is still continuing to run at those conditions. In fact, if you go back to the motor example that Rhett gave, when we have a standard motor running at 100%, these first two are two examples of where that's happening. And then in a bypass situation, secondly, is the unnecessary heat that's being added to the system through recirculation. So I said these are more traditional methods of pump control. The third method we would consider the most efficient method, and that is speed control. And you can see this here. This is the most efficient because we can reduce the speed depending on the demand of the system, reducing the flow whilst not putting additional pressure into the system. But most crucially, we're only using the power that we need. And if you look on the right hand side of this where we've highlighted, you can see the relative power consumption, and this is based on a 20% reduction in flow. So if we reduce the flow, and we're comparing all three of these methods, and so you can see through speed control, the power consumption is well below the other methods of doing that, and that's because we're only using the power that we need based on the demand of the system.
Great. And then the last one would be your full system integration. And here we use controllers with sensors to operate in operation in conjunction with other machinery within the system. So in front of you, you've got a standard and fairly common boiler feed system with boiler water level control, which is controlled by means of a modulating feed valve. And this is then tied back to and integrated with a level transmitter sensor output from the boiler. So your boiler is controlling and feeding back the level that it has at the moment and opening and closing the valve. The modulating feed valve is regulating your water intake, and this is according to your steam consumption. This, however, requires that the feed pump is running set to continuous operation. So the pumps are running continuously, regardless of what the demands on the steam needs for the boiler. The benefits of a system like this is that the boiler feed water flow is adjusted according to the steam consumption, and it's also a tried and tested method of boiler feed control. The drawbacks are that you need to use a bypass in order to take off the excessive flow that's going through these pumps, and you're using then the feed valve maintenance, and the replacement is incredibly expensive in a system like this, and they fail regularly. We're talking about multiple times a year if you are really using that feed valve frequently. And then you've also got the pressure loss across the feed valve leading to a larger feed pump. And then you've got your slow reaction time. These modulating valves, they open very slowly and very close. They open slowly and they close slowly. So you can end up with a system that has thermal shock when the colder water is introduced in large quantities and it's not regulated in a tightly controlled manner. And then you've also got poor economizer heat that picks up the energy. So looking then at what we would want to do in a system like this is, first step is we want to go away from that modulating valve. We want to move towards direct level control based off of the needs of the boiler, and that's fed back direct into speed control onto your pumps. So the level transmitter is fed directly back into your pumps, or otherwise indirectly through the controller on the boiler, and that is then used to regulate the speed at which your pumps are running. As an example, on the left, we've got our motor speed set as a function of input from the level sensor, where we've got 100% speed running out of the pumps when the level is set to low, and when it is full and we've dropped down to, we're up to 20 milliamps or 13 to 20 milliamps, we're recording, at the required level of the system, the pumps are then not running and we're not feeding in more water. So the system reflects and reacts to the demands of the actual system, and we only consume energy in a system like this when it's needed. You still can have a bypass valve depending on whether it's required or not in order to keep your deaerator topped up. But it is something that is per basis depending on the system design. So a system like this also comes with additional protections that your standard modulating valve wouldn't be able to deal with. So what it can do is it can handle a low level alarm and a high level alarm, as well as controls for the remote water treatment of the dosing pumps. The pumps can also feature an integrated graphical display for viewing the boiler level, the pump energy consumption, and the operating hours, faults and alarms can be viewed directly on the pumps. And they can also then communicate directly back with your BMS. So it's an integrated approach that really operates and runs the pumps when they're needed, and the pumps then don't run, or they rather run at a lower speed where they are not needed, or otherwise a small top-up is required within the system. So another way, and a part of the component for intelligent controls, would be to use a pump controller. So as I mentioned earlier, what we want to do is we want to run the pumps such that we are, if it's a high flow system and we need to then traditionally size up to a very, very large pump in order to match that top end required load, what we can do in a case like that is rather split the flow over several pumps. And using a pump controller, such as an MPC CU352, which is a multi-pump controller, you can then start controlling multiple pumps in order to deliver your required flow in the system. So using a system like this in the pumping controller, you get benefits such as built-in control of control systems. So you can have things like pressure control, proportional pressure control, temperature control, proportional temperature control, level control, multiple different control scenarios that are built into the system, and you're not necessarily reliant on a controls programming team that would have to then write this code from scratch. And using a system like this, you can then run the pumps at the optimal efficiency point. Another new method of control for pumps would be something called power optimal pump sequencing. So with a multi-pump system utilizing controllers, they include a sequencing algorithm purely based on pump speed. The number of pumps running is based on the speed of the pumps, and in a set running with multiple pumps, we generally bring on the additional pumps when the pump speed is 85%. So let's say our flow increases, as you can see on the graph in the bottom left. As it increases and we cross 20% of load, 20 meters cubed in the system, we then are needing to bring in another pump in order to reach the additional flow requirements. The problem with this is that you're not running the pumps at the correct best efficiency point of those individual pumps. And the speed-based sequencing, the pumps cannot be guaranteed to run at the optimal power, since the system is only running based off of speed. Using power optimal pump sequencing, what you'll do is you'll actually program in the characteristics of your pump and the curve of the pump per each pump in your system. And using that, the pump is then able to, the multi-pump controller is then able to run each individual pump at the best efficiency point of that pump per the flow required. So looking at a system like this on the left, we can see that while we could have reached almost 30 meters cubed using one pump, we would be then running at a higher power consumption. So at 20 meters cubed, what we can actually do is we can bring on a second pump, and both of those pumps then ramp down and run at a lower speed, and they're running further back on the curve, running at a better efficiency point in order to deliver the flow. And the gains are really quite significant if you compare, looking at 55 meters cubed. Here, a 2-pump system would consume a lot more than a 3-pump system. And this is only really possible to get the best efficiency if you know the curve of your system. With Grundfos multi-pump controllers, this comes pre-programmed within the pumps, and you merely select the pump type, and it then knows the curve of the system, is able to control those pumps to the best efficiency point. And then looking at an integrated control package, what you can then do is you can then take the control sensors within your pumps and feed them back to your pump controller, and you can have them then dotted out along the length of your pump system, and you can monitor multiple different zones within your pump system and react to drops in pressure depending on the consumption per individual zone. Using this method, we can ramp up and ramp down the pumps and ensure that at every single stage, we're able to match and meet the pressure requirements within the system and the demands of those individual zones. If you merely have maybe one sensor on the discharge side, you could end up with a system that is very slow to react to drops in pressure and a poor performance on the users within that system.
And this is running autonomously as well, isn't it, Rhett? These
exactly.
And I think, and again, that's the real beauty of actually from coming to a company actually where I was predominantly only focused on the selection of pumps. This part of it, for a pump supplier, this part of it was something that pump control was something that we were never really exposed to, because it wasn't part of our scope. So actually seeing the type of systems there that Rhett's presenting, it goes again, underlines the earlier part about the importance of designing a system where you're taking everything into control, and that is obviously the system loads, and you really need to have that information when you're sizing your pumps. And so to have controls that are working autonomously, again, coming and seeing this just from only ever seeing one small part of the puzzle, it really does underline the the value that this will bring to to an efficient system.
Yeah.
Sorry, Reckon.
No problem. And then the last one is BMS integration. Really, the days of running a pump at a fixed speed without any transparency on the data and the power consumption of the pump, those really need to be put in the past, because data transparency and the performance reporting on systems is a big focus within factories nowadays. Implementing a distributed control strategy in your pump will allow you to have full transparency of the energy consumption and performance on your systems. What I mean by distributed control strategy is that you have localized control within those systems, such as a pump skid, and that pump skid then knows the energy consumption of each individual component within that pump skid. So using communication standards such as Profinet, BACnet, etc., and a communication card within these pumps, you can then have full data transparency, such as energy, motor speed, pressure set point, and achieved set point that can be easily communicated back to your SCADA or BMS. So why is this important? Well, when you have access to full data, you can start in a factory setting, start logging these data set points and start monitoring the energy consumption and performance of your system. Using that, you can start doing, early detection of issues around maintenance. You can start doing early detection of inefficiency, or maybe a system is running outside of the norm, and we want to then have a look at that system to see maybe there's something that's operating incorrectly. You can also start doing things like energy consumption monitoring over time. So we can see whether we make a change within the system, such as maybe running those pumps a little bit more slowly, drop our pressure set point. We can start doing those sorts of changes and monitoring and seeing what impact that has on the energy consumption of the system. So in a typical pump controller, like we've got on the left, the communication card would then pass through the set points that you see on the right. And you as a factory owner and as an energy engineer, potentially, you can start making informed decisions and logging the data off of your pump systems.
Yeah, and this is an example of a containerized solution and a complete pump skid. The picture on the right that you can see here, this is actually taken from our facility in Sunderland. But this is a really great way to ensure that your pumping system arrives and functions in the most efficient way, in the most responsive and also the most reliable way. Rather than assembly on site with all of the items that are perhaps supplied from several separate suppliers. Actually, a really good example that you might take for this is how in different parts of are items that would be supplied as complete components. We use chiller systems as a good example. You would never get a chiller system and you would assemble this as individual components, because it's not the most efficient way of doing it. You would always have that come as one complete chiller system. And we take the exact same attitude in a lot of cases to complete pump skids. With a containerized pump system, and that would incorporate pumps, piping, VSDs, sensors and controls, and this would be assembled off site. And this would mean that when it's installed, it's going to come pre-tested, it's going to come commissioning ready, in what we would call a turnkey solution. And it has a real advantage for a contractor or an EPC, because from their perspective, this is going to dramatically reduce their workload from a design, procurement and an installation perspective, because obviously this has all been consolidated under one supplier. So you don't have any surprises, so to speak, on site if obviously something can be supplied as one complete unit.
So we've spent a lot of time discussing the energy consumption and design of new systems, and that's really where we want to ensure that any new factory that's being built has got the most efficient pump systems installed from day one. So we talk about then the full integration, talk about looking at what's in the system, how do we communicate with this, how do we ensure that we're only running at the required speeds for that pump system. And that's great. But what if you're working in a factory that's maybe 10, 15, 20, 30 years old, and you've got then pumps sitting within that factory that you're pretty sure are inefficient? Well, the answer is to perform a pump audit on your site. Many companies nowadays offer a basic pump check that will review your asset list, take the nameplate off of the pump, and suggest an equal pump with maybe an IE5 motor attached to it. So the issue with this approach is that you're only really achieving that 10% basic motor efficiency improvement that's available through an IE5 motor, and your return of investment is going to be incredibly low. Whenever we want to invest in upgrades in our pumps, we want to ensure that we're getting the best possible energy savings, because at the end of the day, energy is money within a factory, and if we can reduce energy, we can save the factory money. So using a pump audit with power, pressure, flow measurement equipment, we can ascertain the hydraulic and system performance, looking holistically at how the pump is performing within that wider system. So even if you have fixed speed pumps that you're running at constant speed, and maybe you've got a modulation valve in order to control the flow, using that kind of a system, you might think that it's not easy to get any information on the operation. Well, if we install system sensors such as flow meters and such as power sensors and pressure loggers, we can then at that point start measuring and finding out where your pump in your system is running on its own curve. Oftentimes we find, especially with older factories, the pumps have been oversized massively. And really, when you've got an oversized pump and it's running at a low flow condition, it runs very far left of curve. And very far left of curve is where you get the lowest possible efficiency. So based off of these findings in an audit, your pump, you can define the flow states. So that's the best efficiency point where it's running in different flow classes, as well as then find out where it spends most of the time operating. And using that methodology, we can then look at resizing your pump system in order to have it run such that it is running continuously in the best possible efficiency point on a pump. So the system is resized. You might go with maybe a 3-pump system, and most of the time it runs with only 1 or 2 pumps. And then when you've got a final, the hottest day of the year, and you've got a cooling system, it's the middle of summer, we then bring on that 3rd pump. And then that 3rd pump contributes to an extra flow. But we're not just running one massive pump all the way left of curve. So using this sort of a method, and Gridfrost does this as part of our team, we can then recommend a complete rehaul of the system, and as well as then add control strategies to ensure that we've got the system running at the best efficiency.
Yeah, and as mentioned earlier, industry consumes a huge amount of water. And this puts additional emphasis on how water can be reused and not wasted. We've got a number of examples of this, and we're going to look at a good case in a moment that highlights just how much water can be reused. As mentioned previously, we have a Grundfos company called Euro Water, whose business is everything from groundwater to ultra pure water. As you can see, there are various processes used for water treatment. You have filtration for drinking water, ion exchange for water softening, demineralization, deaeration, polishing. Actually, quite interesting, Euro Water are currently one of the leading companies for water purification used in renewable green hydrogen projects, where water quality is key for producing high quality hydrogen, and ion exchange playing a key part of this process. So it is, as I say, it's really invaluable to our industrial side of our business. And importantly, we do have regulation and legislation in place for minimum water quality, including risk management, permitting criteria that must be met for reused water, and also transparency, whereby the information is available for the public, should I say, for key information where water is being reused. And as I say, we've got a really good example of this. If you want to skip forward, Brett, I know we had another slide in the middle here, but we're gonna move now into some customer cases. Where we're going to just look at some two. We're going to look at this one that we have here for Carlsberg, and then which is around water reuse, and then Rhett's going to show us some with energy savings. But yeah, this is actually one of our flagship projects at Carlsberg, and you can see the top line savings on the screen. This project focus was to take all the process water and send it to a decentral wastewater treatment plant. So treating it in a safe drinking water process to ensure that it can be used again within the brewery. But just note, this wasn't going to be used for brewing this water. It was going to be used for cleaning process. So replacing the water that would otherwise have come from fresh water. And this is using the filtration technology of Euro water that I showed previously. I mean, as I say, I mean, 90% is a huge number. And as I say, earlier on we mentioned that we're heavily focused on the utility side, and like I say, this is water that would otherwise have come from fresh water coming in. So the fact that we can reuse over 90%, we're talking big numbers here. And Carlsberg, they've actually got more than 80 breweries around the world, and some of them are in sort of water scarce areas. And so this has got the potential to be implemented everywhere. And I'm sure that there are a number of you on this call who enjoy drinking beer, but I think I'm not sure how many people will be aware of how much of a water intensive process just brewing as a whole is. And so there's about 3.5 litres of water required to produce 1 litre of beer, and that's sort of a global average as of 2015. And what Carlsberg are trying to do is they're actually trying to reduce this number down by 50% towards the end of 2030 to bring that down from about 3.5 down to about 1.7. So it's as I say, it's a flagship project, and this is something that with our projects, and I'm sure with our customers' projects, we're going to start seeing deliverables around water reuse and energy savings because of the carbon emissions associated with those. They're going to start. We're starting to see them now. More and more they're coming up. That we do have to reach deliverables for projects where we can evidence energy savings and water savings, etc. And that the energy audit that Rhett showed previously, this has become that's actually traditionally that was a tool that we were using in existing installations where we could show energy use, and then we could show where we could actually save, optimize on the pump systems and save that. We're actually starting to bring that tool in more and more, so we can start on new builds where we can say, look, these are the traditional methods of doing things, and this is how we can actually save with an optimized pump system versus a more traditional system. So really useful tools, and there's a lot that we can do.
Right, another good one for you based in the UK would be Suntory, which is a food and bev manufacturer within Great Britain and Ireland. So what they had was an issue whereby they knew that they had inefficient pump systems within site. As part of SPTI, the group had been told, the different factories, that you need to find projects in order to reduce the energy consumption on site. And their targets was to achieve a net zero by 2015 using 2015 as the baseline, with a 50% reduction by 2030. So they got into touch with Grundfos. They had lots of really outdated systems. What we did was we worked with them to try and find the systems within their factory that would give them the most return of investment, so the least efficient systems, overhaul those, monitor them, resize them, and do a new installation at the factory in order to find then and give the most amount of reduction in energy and carbon emissions per system. So we used our IE5 motors, which have built-in variable speed control, and they operate on demand with the pressure control and temperature control depending on the application, meaning that the pumps only run when the system needs. So we provided a full turnkey installation and package to Suntory, and this resulted in between 40 and 60% energy savings with every project that they were looking at that we had kind of suggested. And they've just moved throughout the site's different areas to optimize the pump systems within the factory. Another great example would be Rolls-Royce. Rolls-Royce in Inchinnan, they are a aerospace manufacturing group within Rolls-Royce Group. And a lot of their machinery that they have on site are machines that are CNCs, and they are machining these incredibly complex parts that go into the aerospace industry. And what they wanted to do was to reduce the cooling energy consumption that they had on site to cool down these machining machines. So what they had was they had uncontrolled pumps that had a huge influence on how efficiently those cooling systems were operating. And what we did is we did, again, an energy optimization audit on the site. We found out which systems are running maybe a little bit too hard relative to the cooling requirements. We also look at, and then the chiller components and the systems that are meant to control the temperature within Rolls-Royce, and we suggested different changes to the control strategy that they had. And we resized and reduced the size of the pump at Rolls-Royce, and we ended up with a 225,000 euros reduction in energy consumption on site. And this is all done again with new control modes that were added to these uncontrolled pumps, and they automatically stop when they're not running. So when they're not necessarily running a set of machines, the pumps switch off. No need to run coolant through them because we're not generating any heat. So that's the holistic approach that you can get and the savings that you get on a site like this. Another one would be, again, a soft drink manufacturer, Britvic. What they did was they looked at using an on-site energy audit that boosted the system performance for the site. And what they initially had was that they wanted to reduce the energy consumption on site. And what we were able to do was to resize and give them an expandable solution that, first of all, reduced the energy consumption by 45%, but also it allowed them to, because they were consuming less energy, they were allowed to then able to then add an additional manufacturing process within the factory and not increase the overall energy consumption on site. So what they went with was this containerized solution. So they had guaranteed performance. It was installed on site. And what it did was then it was pre-tested. It was a quick and easy installation, well, as easy as possible, because generally when you're dealing with sites like this, they have incredibly short shutdown times. So going with a controlled package like this, you're able to then reduce your installation time dramatically because you really just need to drop in the system, plug it in after removing the original one, and it's up and running, and you have your controls already integrated. Great. So what we can do then is, how can we help? Charlie, I'm going to maybe hand over to you here.
Yeah, I mean, this is sort of our wrap up from us, really. But to say we've covered sort of the key areas really for sustainable operation and optimized pump systems, and the way that we want to do this, as I say, we've focused on the key areas of water reuse. Like you say, when you actually look at a facility, I think the general sort of immediate focus sort of looks towards a process. But as I say, the utility side, it's a big consumer of both water and energy, and so that's really why we wanted to focus on these areas and sort of show the real value in controlled intelligence and explaining what we mean by controlled intelligence, which is a sort of, as Rex described really well, a system that's reactive and running autonomously, and making sure that we're constantly running it in the most optimized position as we possibly can. And so there are lots of different focus areas, as we touched on, that contribute to this, and these are all the areas, again, to bring it back to Grundfos and why we're sort of quite successful at what we do, is because rather than just being a pump supplier or a control supplier or a VSD supplier, being able to see the whole installation and understand exactly what the customer's trying to do, how the demands of the system, and not breaking this up into various things and then trying to assemble it as one. As a whole, it means we can support and consult on the design of the system, and we're involved all the way through the system design, all the way through to installation. And that, as I say, we know that by being able to sort of touch all of those areas all the way through, that once it gets onto site, it's gonna run on an optimized and also a reliable way. And again, from the water reuse perspective, the same applies. Being able to be involved in the design phase of it, understanding what the customer's trying to do, and we do this very regularly. We consult in such a way where they'll give us the information, and then we can reach out to companies like Eurowater and IMechE, as I said before, they're experts in water, and what they can bring to us as has been so much more than just a product. The knowledge that they bring to Grundfos and their experience, as I say, across the board. From everything from food and beverage all the way through to hydrogen. It's a depth of knowledge which has given us as much value as the product itself. So, with that in mind, does anybody have any questions that they would like to add?
Hi there, it's Martin here. Can I just come in and basically say, as we've got a shortage of questions here, so I'm going to ask one myself in a minute. But please, if you have a question, please put it into the Q&A box, and we'll do our best to answer it. Any that aren't done in the time, we've got about 10 minutes left. We don't mind running over a few minutes, but anything that isn't answered, we can answer later. Okay, so my question really is both for you two and for Pamela. Pamela works for United Utilities and is a mechanical engineer with them. I've always found a problem with utilities, water suppliers, and they have two main problems: meeting the high flow rate at peak times, and also pressure differences between daytime and nighttime. You could have 2 bar during the day and 4 bar at night and things like this. So it's very difficult to control process systems. And I'm assuming that your system now can overcome this.
Yes. Absolutely. So in that sort of a case, Martin, what you would want to do for a high flow system that's got variable flow is you would split up the flow requirements into multiple pumps, and then use a controller to switch on and switch off those pumps. And as the flow demand increases, so does your the amount of pumps that you run in order to provide that flow throughout the system. And then the second one would be to use a system and a controller that is actually able to input and change according to the requirements on the system. So if your central, let's say your BMS knows that at a certain time of the day, you need 2.5 bar worth of pressure, or let's say 3 bar worth of pressure, and then at night time you need 2.5 bar worth of pressure. If you pass that information down to your controller and change the control set point on the pump controllers, they'll just update their target and their running speed in order to match that new pressure. So as long as you've got a pressure sensor within the system, you pass down the required set point, it can then adjust the pressure set point that it's going to be running those pumps to. So that should solve both of those issues if you go with a multi-pump system.
And that graphic, I don't know if you can jump back to it, Gret. That's a video graphic that we have of the system where it's automatically updated. That's doing exactly what we're talking about. There you go. That's the one. So yeah, I mean, this is a system the same as any other system, where it has highs and lows demand depending on in this case the time of the day or night. And as we mentioned, I mean, that again, that's one of the beauties of having an intelligent control attached to it, is that it does it autonomously, as Rhett said, so it can adjust the pressure depending. And this is where you make those efficiency savings.
Yeah. Okay, well, thank you. Pamela, have you got any comment there?
No, sorry. I'm sorting out the chat. Sorry.
Yeah. It's okay. Just basically, United Utilities and other utilities companies must use these systems now to good effect, I guess.
I don't know of many, to be honest, Martin.
Okay.
In the water delivery side, I don't know of many, because we don't have many systems. We will have some that use multiple pumps, so it tends to only be 1 or 2 pumps, and then we have a standby. So it's how much optimize it, because the optimization equipment must cost an amount in the first place, and it's to put in that infrastructure we need to probably better assess how much of the savings we could get by installing that capital delivery equipment in the first place.
Yeah.
How much savings.
I think, Pam, you've touched on a really great point there. It's all back to return of investment. If you're going to be modernizing the system, you need to ensure that you have the return of investment that that guarantees that, you're going to get money out of the system. You're saving energy. How long is it going to take me to pay off this investment? So that's something that generally in industries we see about between 3 to 4 years return on investment. Some factories, they require a little bit less. Some factories are happy with a little bit more of a return on investment, and that sort of defines whether the project's going to go forward or not at the end of the day. And that really ensures that your factory is putting their money where it should go. So that's why when I say we work with a lot of factories, but we don't necessarily optimize the entire factory, because some systems you're going to have marginal improvements in efficiency. So then you're going to have marginal reduction in energy consumption. And at the end of the day, if it doesn't make sense financially, it's not going to go forward. So when we look at optimizing a system, generally we see between 40 and 70% energy savings being a very good benchmark, which would say, yes, we can probably get a good system in here. And we can save money for the factory, and they can reduce their energy consumption and keep their return on investment under that maybe 3 or 4 year benchmark. I hope that sort of answers it. The multiple pump controller that we see here is more seen. Well, we work primarily in industry. This is seen on the utility side, where they've got big swings in production. They might not run a night production. They might have a higher cooling demand requirements in the summer versus the winter. So here, when you've got big swings in your flow and big swings in your pressure requirements, you can then add these sorts of controllers and get a really attractive return on investment.
Okay. Well, thanks very much. Could you put up the next slide, please? Oh,
Fine.
my next slide.
Oh, yeah.
So, Martin, there are some questions in the chat. There are some more questions.
Okay.
Yes.
Oh, in the chat rather than Q&A. Okay.
No, sorry. They are in the Q&A. I moved them across.
Okay.
Martin, could you read that off for me? I just can't see it at the moment.
Okay, I can't see anything either. You.
Right. I can go through them then. Yeah.
Okay,
Somebody put in the chat. Can your sensor
Oh, yeah.
systems work on an offline closed network?
Absolutely. Yeah. So that's actually a great benefit of a Grundfos system, is that it can operate completely on its own, be it programmed directly on the pumps or on the controller, and you don't have to network back to anything. So you can set this as a distributed control system within your system, and it can operate completely independently without any requirement of feedback from a BMS or anything like that.
And then another question. In the wastewater treatment, we do a lot of like-for-like replacement, where there's often space restrictions when retrofitting. So not feasible to install an additional pump. What is the best approach to selecting the new pumps in that situation?
So wastewater systems, the best method in order to reselect your pumps would be to really get an understanding of where they are operating. So what we do is we do that energy consumption monitoring, we do flow monitoring on the systems. We come in and we install that hardware on site, and we then monitor, maybe 2 weeks, depending on the complexity of the system, maybe 4 weeks, and we define then the flow classes of those systems. Generally, wastewater systems, they aren't going to have the biggest energy savings because they're not necessarily going to be running all the time, and the requirements and the changes aren't that large. But if you want to resize your system, it starts with understanding how it's operating within that. And then what you would do is, if you find that the pump is oversized, you would simply resize the pump downwards. And even reducing the size of the pump and putting it such that it operates on a better efficiency point, that's going to give you savings on its own. You don't necessarily have to always split the flow over multiple pumps, but you can rather just ensure that your maybe 2 pumps that are operating at the correct size. So reduce your motor size, maybe have a smaller pump hydraulic so that it's running more efficiently, and that's going to give you good savings at that point.
And those integrated VSDs, I've actually come across this a few times myself, and that again, in addition to obviously reducing your pump size, something that we talk about a lot at Grundfos is reducing system complexity. And that's where, that's where the integrated VSDs can be connected to directly to your sensors. So you wouldn't necessarily, in some cases, need to have, external control panels or everything like that. That control can all be consolidated into the VSD itself. So, so you not only in that, what Rhett was saying, downgrading the size of the pump, but also you might be able to reduce your system complexity, which we see quite a lot of.
Can I just ask you to put the first of the IMechE slides up, please?
Yep.
Okay. All right. So while Pamela carries on with the questions, just take a look at this slide, please. It's some of the upcoming webinars we've got coming on at IMechE. So not to waste any more time, let Pamela carry on.
Yeah, sorry, just one last question. So we have an existing pumping system. What is there a typical kilowatt rating where you could look at it to see if the savings for the power consumption would outweigh the cost of the optimization equipment controller?
That's a really great question.
Kilowatt.
Yeah, that's a really great question. So generally, the more savings that you're going to find are on the larger pump systems, because what we do find is that, the larger kilowatt motors on the large pump systems, they're probably the ones that are sitting with one pump doing the full, duty requirement and one in standby. So those pumps are generally going to be oversized for the application. So if we're talking like, I would say 11 kilowatt and above, you might start looking at those pumps. And, we deal with pumps in the order of hundreds of kilowatts, and we resize those and reduce the size of the motors by tens of kilowatts in resizing them. So as a benchmark, you want to start sort of 11 kilowatt and above, looking at those pumps, but that's not necessarily to say that your smaller pumps aren't going to give you that return of investment, because those pumps are actually normally quite easy to swap out because they are generally smaller. So it's all about looking at really how inefficiently are those pumps running. And you can tell a little bit, if you're just walking around at your pump system and you hear, let's say, cavitation on the pumps, that's a really good example and good kind of alarm bell that should be going off to say that this pump is probably running inefficiently according to the demands. And that's then when you would say, okay, let's stop, let's have a look at it. How is it running? How is this pump size? And what are the requirements that we actually need out of the system?
Thank you. Have we got time for one more, Martin, or not?
I think not, actually. I'm just thinking that the numbers are starting to drop off now. So I think we ought to basically close it. And if it's okay with you, Rhett and Charlie, there's a couple of questions still on there. One from John Whiting, and Pamela's got a couple of questions. I think what we should do is maybe answer them afterwards. If you can take a look at the Q&A and answer them afterwards. Okay.
Yeah, these have been good questions, so we'll capture those. And we'll send out the presentation for everyone to look at in their own time, and we'll answer those questions in a Q&A document attached to the presentation.
Yeah. Okay, so I'm going to start one up. Firstly, to say thank you very much to Charlie and Rhett. It's been a very, very interesting and fast-flowing presentation, covered a lot of ground. And so the numbers are dropping off, so I want to make sure that you get everything you need. There's a final slide here. If you would like a CPD certificate, then please email Murat at the address on the page there, and please, if you can, fill the event feedback form. We'd like to know what you think of these presentations and how we can improve them in the future. So, okay, let's leave it at that. Thanks again to everyone, and so we'll ask the outstanding questions offline. Thank you very much.
Thanks very much for having us.
Thank you. Thanks, everyone.
Thank you. Okay, yes. Okay, Pamela, do we leave or end meeting? What do we do now?